Okay. So the title of my talk is the Forensics at NIST Workshop. And I'm going to talk to you about some different ways of dealing with mass spectral data, not just doing library searches and other things. So when you sit down to solve a problem with GCMS, where do you begin? What is the starting point? And the starting point, I think, is in the mass spectrometer tuning. Now, a lot of you don't pay a lot of attention to the tuning. You just tune the instrument. Some of you tune it when you see data that doesn't look right. Some of you tune it on a regular basis. But the M over Z range is going to have to be tuned, and the intensities of the various ions are going to have to be tuned. Now, all manufacturers don't tune the mass spectrometers in the same way. Agilent's auto tune sets the base peak for the compound perfluoral tributylamine to be M over Z 219. This is the standard tuning compound. Well, the mass spectrum for that compound has always had the base peak at 69. The Agilent manual tells you that if you are going to do a library search, then you should use the standard spectrum tune. And this is because some time ago, Agilent changed their routine auto tune to be that of what at that time was called a high sensitivity tune. And they took the old auto tune and changed it to be the standard spectrum tune. So all the spectra that are measured at NIST are all measured with perfluoral tributylamine having a base peak of M over Z 69. Now, most other GCMS manufacturers tune to this base peak. Thermo Fisher does, Shibatsu, PerkinElmer, and Psion. And all spectrum always acquire spectrum of PFTBA at the start of the day and do a visual evaluation of that spectrum. Why is this an issue? The reason it's an issue is all the spectra in the NIST library are acquired by NIST using the standard spectrum tune. Now, what is this difference? On the top is the standard spectrum tune, right? And we see 69 as the base peak, and we see 219 about 60% of 69. The high sensitivity tune, which is now called auto tune by Agilent, has 219 as the base peak, and 69 is about 80% of 219. And this is so you have higher intensity at the high end of the mass spectrum to help you meet the sensitivity specifications that Agilent specifies. Okay. And again, all spectra acquired by NIST using Agilent and MSDs are acquired with standard spectrum tune. And as a matter of fact, all the spectra acquired for electron ionization library at NIST are acquired using MSD. Perfluorotributylamine is used for the calibration of the M/Z scale because of the mass defect of fluorine as compared to the mass defect of hydrogen. You see, there is a considerable difference. Therefore, the exact mass, even at high mass, of a perfluorinated carbon ion is going to be very close to its integer mass. Data acquisition guidelines. Where should you start your acquisition? Start the acquisition at M/Z 10. Don't drown in water or be suffocated by bad air. You want to see these peaks at M/Z 18, M/Z 28, and M/Z 32. Let's see, somehow we because these peaks indicate that you have leaks in your system someplace. And water and oxygen can be very detrimental to the stationary phase of your column and reduce the life of your column very easily. So also there are important ions that occur at M/Z 30 and M/Z 31 for aliphatic amines and aliphatic alcohols. And if you start your acquisition so that you avoid air and water peaks in the mass spectrum, then you are going to run into a problem with not seeing these ions for amines and alcohol. Also, even if you do have small leaks that you allow to continue and you process your data with AMDIS will remove those ions from the deconvoluted spectrum. Adjust your method for greater than 7 spectra over the RITC chromatographic peak of a pure compound. This may require that you have different settings for different ranges of the chromatogram, especially when doing temperature programming. Data should send retention index with the spectrum to NIST Search when you are sending it from AMDIS. This is going to require that you do a measurement of a retention index standard at the beginning of each day. When NIST acquires Spectra, they create this file for retention index. Data files should be processed using AMDIS in order to get the poorest spectra. AMDIS hasn't always been available. We use other techniques, which I'm going to talk about, but today there's no excuse not to use AMDIS, and AMDIS can easily be used with data from any manufacturer's instrument. Okay, also make sure that you have programmed into your method an appropriate filament multiplier delay to keep from shortening the life of these two important devices in your spectrometer. Okay, now let's take a look at some real data so that we can see some of the possibilities that we can use. Now, the first thing we're going to look at is we're going to look at a story that I found very interesting. Okay. All right. I want to tell you about my erstwhile brother-in-law, Billy Bob Bodecker. Billy Bob Bodecker worked for a chemical manufacturing company in Houston, Texas. One Friday afternoon, he was going to leave on a 2-week vacation from Houston, Texas to Yellowstone National Park in an old 1958 Chevrolet station wagon with his wife, my sister, and their 3 children, the youngest of which was 9 months and the oldest of which was about 3. Just as the clock was about to strike the end of his shift time, his boss called him and said, "Billy Bob, you've got to identify this compound for us. We have a 500,000 gallon storage tank full of this material. If it's one thing, we can rework it and it'll be the financial salvation of the company. If it's another thing, then what will happen is we'll have to dump it into the Houston Ship Channel by the dark of the night because we can't afford the remediation." Now, Billy Bob said, "No, I don't have time to do this. I'm leaving on vacation. Get the night shift guy to do it." And the boss said, "We hired you to interpret mass spectra, so you're going to do it. And it's fairly simple. It's one component in a mixed chromatogram." So he said, "Okay, what is it? What component do you?" And they said, "That component is located in this series of chromatographic peaks." Now, all of these peaks look very nice and symmetrical. These 2 peaks have some coelution, as Gary Ballard described earlier, but you would expect that each one of these peaks would possibly be a pure compound. So he did what many people do, is he went to the apex of the chromatographic peak, displayed the mass spectrum. He looked at the mass spectrum and he saw that it was not going to be easy to interpret manually. Here is a peak at 1 m/z 117, 119, and 121. That could represent an ion with 2 or 3 atoms of chlorine, maybe 3 atoms of chlorine. Now here's another peak that is 90 at m/z 97, and that peak is 20 m/z different than 117. 20 could easily be the loss of a molecule of hydrogen fluoride, which would indicate that this was a nitrogen-containing compound. The fragment ion retained the nitrogen, but the problem is the isotope pattern changed with the loss of 20, and that is not possible. So he said, "I'll do the next best thing. I'll do a library search." So in the Agilent software, at that time it was HP software, you could double click on the mass spectrum and you sent, let's see here, you sent the spectrum to the NIST Search program. Now, one of the things you're going to notice here is my version of the NIST Search program looks a little different than other versions of the program that other people have shown you. That's because the program can be easily customized by putting your mouse pointer in any window, right-clicking, and selecting properties. And you can do things such as change the fonts. And once you've changed the fonts for one window, you can also specify that you want to change the fonts for other windows. These columns that are in the hit list here are all adjustable, and you can come along here and drag one of these points across to make it wider or less wide, and you can delete the display of various columns. You can also easily change the size of the windows. One of the things that I've done here is that, and it's interesting because when I'm sharing this, I can't make these adjustments. I can change these various size windows. Sorry, I can't show you that, but it seems to be something to do with the blue jeans display. But anyway, this was the result that he got. And what he had from searching the NIST main and rep libs, he had the first 5 hits all for the same compound, 1,1,2 trichloral ethane. Now, these had match factors that were not particularly high, but still fairly respectable. And the probability of having matched the sample spectrum against the library spectrum was 81%. Therefore, he picked up the telephone and he called the boss and said, "Boss, this results is 1,1,2 trichloroethane." Okay? And slammed down the phone, ran out, and went on vacation. Came back 2 weeks later, pulled up to the gate. It was pouring rain. If any of you have ever been in Houston, Texas, you know what rain's really like. It was pouring rain. He stuck his key card in to open the gate and work. And he saw a big water-soaked box that had a plastic envelope in it that had a letter that said, "Billy Bob, you were fired." Now, where did Billy Bob take a left turn that got him fired? Well, Billy Bob only looked at the hit list of this. He didn't look at the spectrum. Okay? And what happens is if I take this first hit here, and compare these spectra, I see that there are quite a few differences. The library spectrum has a cluster of peaks at 132, 134, 136, which is missing in the sample spectrum. The sample spectrum has a cluster of 3 peaks representing 3 atoms of chlorine that is not in the library spectrum. The library spectrum has a base peak And it's hard to tell. It looks like these two base peaks are close to one another. But if I look here, the library spectrum has a base peak at 83 and 97 is the base peak. In my sample, 83 is the base peak and 97 is the lesser of the two intensities. That should have made him suspicious. And he should have returned to the original data file. Well, my system seems to have.
David, maybe you want to try stop sharing and sharing again, because it seems like your mouse is delayed from your screen share anyway.
Okay. So let's.
But I'm at the edge of my seat. I want to know what's happening with it.
Well, it is an interesting story.
It really is.
Okay. Okay. I'm able to bring back up the original data file. Okay, now remember, this is what we're looking at. Now, let's look at this mass spectrum. Let's look at this chromatographic peak. Let's look at a spectrum on the back side of the peak. All right. Now, you see, we have a result here that does not have a 3 in it. And on the front side, we have a result that does not have the 97 in it. And if we look at those two spectra together, we see that those are two definitely different spectra. Okay? And what we're going to do is we're going to look at mass chromatograms, or as some people call them, extracted ion current chromatograms, of 83 and 97. And when we do that, we're going to come up with 97 and 83. And we are going to look at those two merged together. All I have to do is find the and if you look at those chromatographic peaks, you'll see that they definitely represent two different compounds. So what I'm going to do is I'm going to take the spectrum that is represented by M over Z 97, and I'm going to subtract from it this spectrum for M over Z 83, And then I'm going to send that spectrum to the NIST program and do a search and look at the difference in the match factors here. And the compound is 1,1,1 trichloroethane. And if I do the reverse in the subtraction, then I am going to end up with the spectrum for chloroform. Now, this is a powerful tool that we have in doing searches, these background subtractions. But no longer do we have to do that because AMDIS would have separated those two components easily. Now, there are a couple of other things that AMDIS does that I particularly like. One of them is I'm going to go back and here is another data file. One time I was teaching a course and I was told that within this cluster of peaks, there was a spectrum that they wanted me to interpret. And they said it was at about 9 minutes. So I went to the top of this chromatographic peak and said, well, is this what you want me to interpret? And they said, no, we want you to interpret the spectrum at scan number 561. Okay. Well, I said that's very challenging because look at what a low total ion current that spectrum gives. But as I looked at that spectrum, I saw a number of things that were very interesting about it. One of the things was there were several peaks, 207, 281, and 355, and 429. Those peaks are indicative of GC column plate. I also saw that there was a fairly intense peak at M over Z 232, which could be a molecular ion peak. And if it was a molecular ion peak, it was probably that of an aromatic compound because aromatic compounds give intense molecular ion peaks relative to other peaks. There was another peak at M over Z 270, at 72, and that is an even value, which could be a fragment ion that contains an odd number of nitrogen atoms, which means that the molecular ion, if 232, based on the nitrogen rule, would be an ion with 2 atoms of nitrogen. So I decided that what I would do is I would do mass chromatograms of 232 and 72. So I go up here and I put in 232 and 72. And let's see what I do here.
I think you typed in 272 instead of 72.
That's right, I did. Okay, no problem. And we're going to go here. All right. And what we see, let's overlay those two. And we see they overlay here. And this is the one that I'm going to take as a spectrum. And this is the one that I'm going to take the spectrum for the background. And then I'm going to do the subtract. And you see how much this cleaned up? Also notice there is a peak here at M over Z 213, which is 19 difference than 232, that indicates that it may contain fluorine. So I've got an aromatic compound that contains 2 atoms of nitrogen and contains fluorine. So I'm now going to search that spectrum against the library, and what that comes up with is this is my first hit. Now, this match factor is not very good. The probability is very low. The only saving grace here is the reverse match factor. And the reverse match factor is a match factor that is calculated disregarding any peaks in the sample spectrum that are not in the library spectrum. So this could be an answer, but this is really not very good in terms of coming up with an answer. So what I'm going to do is I'm going to see what I can do with AMDIS with this. All right. So I'm going to go back to this, and I'm going to take the spectrum or the data file, and I'm going to send it to AMDIS. Okay. And here comes up and I'll take this section and remember that our component is down in this region, and I let AMDIS process it, and well, I've somehow lost it.
I think you said it was scan 561.
Yes.
Just a little bit to the right of where you are.
Okay, no, that's not it. There it is, right there. Okay, so now I found that spectrum again, but AMDIS has cleared it up, and I am going to send it to the NIST Search program and let it be searched there. And look at the improvement in the match factor and look at the probability now that I have identified. So AMDIS did a much better job than I could do in doing an identification on my own. All right. Now, let's take a look at another example of the power of AMDIS. Okay. That's a pretty nice looking chromatographic peak, isn't it? If I look at the spectrum at the apex, it indicates that there's a possibility that there's one or more atoms of sulfur present here because of this very intense X+2 peak. Okay, if I do an average spectrum here, it still indicates that sulfur is present. But the best thing to always do is look at the two sides of the chromatographic peak. You see that very intense X+2 peak has disappeared. And here it is more intense. And so what this is this is representing possibly two different compounds. And if I look at those two spectra side by side, I see, yes, indeed, they are different compounds. Now, those spectra are so close to one another, I have no way of manually doing a background subtraction to come up with a spectrum to possibly search. But I can send that spectrum to AMDIS. Okay. And I'm going to, all right. And now I'm going to let AMDIS do this. And I'm using a library here. And you see, let's open this up a little more. It identified two separate compounds. One of them is 3-chlorophenol. Another possibility would be 2-chlorophenol. And then the other compound that is naphthalene. And what I want you to do is I want you to see that this spectrum has a retention time of 10.160 minutes. This spectrum also has a real retention time of 10.160 minutes. But NIST has an extracted spectrum time of 10.161 for the second compound, and for the first compound, 10.159. That is, and it has separated those two compounds, and from the data that NIST created, you can quantitate those two compounds. Okay, so that gives you an idea of some of the various applications of NIST that you can use. Now, I and Jim only look at gas chromatography mass spectral data today using NIST. We immediately open the file, we run the automatic deconvolution, and we take the components from it for identification. Okay. Now, I want to talk to you a little bit about the hybrid search. Okay. Here, here is a spectrum that was sent to me for identification. Now, if I look at this spectrum, I see that the peak at 248 is a pretty good possibility for a molecular ion peak. So I'm going to take a chance and say that is the difference. And if I come along here and set up my library search parameters,
Yeah, it's interesting, David. It seems there's something wrong with your mouse in MS Search because it doesn't click where you think it is. It's like always a little bit below where you think it is.
well, one of the things, Aaron, that it's not doing is
Yeah, I wonder what that is. It seems like you're...
okay. What I'm going to do is I'm going to try to close MS Search. And okay. And now I'm going to reopen it. All right.
Yeah, that looks better.
And that works.
There you go.
Now we've got it working. Okay. So I'm going to go here and I'm going to do a hybrid search, and I'm going to specify the molecular weight as being 248. Now, remember Jim told you that if you don't know the molecular weight, you can do chemical ionization. But something else that you can do to determine molecular weights of compounds due to the molecular ion peak is to do derivatization. All right. So now I'm going to search this spectrum against only the main library in NIST. Now, first off, what I'm going to do is I'm going to do a normal identity search for this spectrum. Okay? And let's do that. And you see our first hit comes up here being 568 as a match factor. The reverse match factor is 671. The probability is 18%. That tells me pretty much that there is not a spectrum that is close to matching this spectrum in my library. So now what I'm going to do is I'm going to do a hybrid search on this, and I'm going to specify 248 as the molecular ion peak, and now I'm going to end up with a hybrid spectrum, same hit, but look at the hybridized match factor. It is now 813. Now you see, I told you my display was different, but if I come along here and show the compare pane, now you see the hybridized search results. Also, if we look at this, now you can see I can change the widths of these columns, which is a very convenient thing. I can pull these down. All right. And I can change this. And I can also change the orientation of the splitters, as we've done here. And we have the metadata here for each spectrum here, and the splitter bar is here. I personally prefer to have it as shown here. Now, I see that the delta mass is 16. What is the number 16 besides the age of my youngest granddaughter? The first thing that comes to mind for me when I think of 16 is oxygen. So what I'm going to do is I'm going to adjust this structure. And I'm going to take this structure and I'm going to copy the structure to the Windows clipboard. Then I'm going to go to my drawing program. I'm going to paste that structure in. All right, there it is pasted in. And now what I'm going to do is look at where you could add an oxygen. Well, we had some other data for this compound, and that other data was infrared. And when we looked at the infrared, we saw that the compound was probably an ester. So if I come along here and I'm going to put an oxygen in here. Now, unfortunately, it looks like I'm going to have to open this again because I'm having the same mouse problem with this program that I had.
Yeah, it seems like the same issue where your mouse is not where you think it is. Like, bizarre.
Okay, that window is closed. I'll reopen this. I'm going to put an oxygen here to create an ester, right? And then it's going to be, you see, it's 16 different. So it's probably going to be something like this, that it's an ethyl ester. Now I'm going to take this, copy that structure, go back to NIST Search, go to the librarian program, come to this, edit this, and then add the clipboard structure, and then add this to the spec list. And now what I'm going to do is send that to MS Interpreter. And look at that. Look at how closely all of the peaks match for this as the possible structure. There's a little bit off on the isotope peaks. This red peak indicates that this is an ion that there is no method for or rule for, so it can't be taken into account. But with the majority of the peaks here, I would say this was the correct answer. And as it turned out, we were able to go to a clandestine chemicals database, find this compound, and get matching data from another agency. So these are some of the things that you can do with all of the tools that are in NIST. Now, one of the things that Arun asked Jim about doing this particular problem, after I saw the infrared spectrum and saw that it was an ester, it took me about 10 minutes to come up with this answer and send it to my client. And my client was able to come up with the final answer in an hour. So these are some of the powerful things that you can do with NIST, both the search program, the hybrid search is just one of the greatest things in the world because it greatly extends the breadth of your library. And then you can take spectra like this with these structures and save them into your user libraries. All right, I have no idea how much time I've taken, and so I'm available for any questions that you have.
Awesome. Well, thank you so much. I actually don't know what the schedule is supposed to be either, so I'm hoping Ed will pipe in and let us know.
Yeah, I would say let's take 15-minute break. We'll come back at the top of the hour and we'll do an hour. We'll get to the questions that were here for David. We'll go back to some of the questions from Gary. Answer questions. So we'll see everybody back at 3.
All right. Everyone get a stretch in and then bring all your good questions.